All right, so we are going to jump right in and continue. Well, not quite continue. We're going to continue talking about circuits. So today we're going to start by talking about electromotive force. Right. So what you guys might remember from last week, from last lecture and the lecture before, is that a voltage difference produces a current flow. So the only way that you have charges flowing is if you have some electric field that forces those charges to go from point A to point B, that applies a force to them. And the only way that that electric field arises is if there's a potential difference, an electric potential difference between the 2 points. So if you have an electric potential between 2 places, say on a conductor, that potential is the result of an electric field, or vice versa. They're kind of yin and yang in that regard. So that electric potential creates an electric field which pushes the electrons or the charges to flow in whatever way they would flow. So that's what causes a current. So in capacitors, the voltage differences are a result from the charges being separated, right? So in order to create the voltage difference between the 2 plates on a capacitor, you have to just take charges from one plate and put them on the other. But in order to do that, that requires currents to, or that requires charges to move. Hopefully I'm not cutting out. Right, that requires charges to move. And so in order to establish that voltage difference, that potential difference, you had to have moving charges already. So it seems like it's kind of cat eat tail, or whatever the phrase is, that in order to create a potential difference, you need to have charge flow, and in order to get charge flow, you need to have a potential difference. But in fact, that's not the case. So to establish current flow, or to establish a potential difference, without current flow, or without being caused by current flow, we need something else. We just need something that breaks the loop. And so what we do is we introduce this notion of the electromotive force. Put an underline under that. It is a technical term. And it is often abbreviated just EMF. Now notice, by the way, that it'll often be abbreviated in lowercase letters. Not quite sure why, but that's kind of what's done. So if you want to call it an EMF, that's fine. Note that it does not stand for electromagnetic field. Does not stand for that. If you ask any 9C student what EMF stands for, if they say electromagnetic field, they haven't learned anything. So it stands for electromotive force. So the electromotive force is not a force. It's just poorly named, I'm sorry. It's a thing rather than like an abstract idea like a force. So an electromotive force is a source. It's some source of potential difference that is self-sustaining. And so there are a bunch of different kinds. There are lots of different sources of electromotive force. Some of them are chemical, so that would be like batteries. You might see magnetic sources of the electromotive force, and there are others. But these are probably the 2 most common. You have chemical in the form of batteries, and you have magnetic, or really it's electromagnetic in the form of like generators. But really that magnetic source comes from mechanical work and so on. But regardless of where that electromotive force comes from, we call them all the same thing. We call them all batteries, at least for now. So anything that has an electromotive force, and a thing has an electromotive force. It's not, typically force is not something that something can have. When we're talking about actual forces that Newton talks about, this is not actually like a force in that sense. So a thing has an electromotive force. It's kind of basically like a voltage. And so a battery produces or has an electromotive force. And we label, whenever we're talking about the EMF of something, we label the EMF by the letter E. And that's not an epsilon, that's a capital curly E. Again, sorry for the overburdening of notation. It's just what we use. And so we started this discussion by indicating, yeah, it's a curly E. We started this discussion by indicating that this is a source of potential difference. And so the units of this curly E, notice that is capital. If it was an epsilon, it would be like lowercase. It would be smaller. The units is just volts. So if you wanted to say, describe the EMF of a battery, you would say that its EMF is 5 volts. And what that means is it just has a constant potential difference across it of 5 volts. It doesn't matter what is happening, whether charges are flowing into or out of that battery or whatever, it will always have that potential difference. One way to think of this is kind of like a pump, like a water pump. Like if you put a pump in water, there will always be a pressure difference between two sides, regardless of how much water is flowing through. So you can think of an EMF as just like an electron pump. It just always, if an electron goes in one end with some potential, it will come out with however much more potential that the EMF is given by. So you can think of it as kind of like a capacitor that never runs out of battery or never runs out of charges either. That would work just as well. That's a little bit of a broken analogy. So the reason why we introduce this is that we want to be able to have some sort of non-empty or complete circuit. And when I say complete, I just mean a circuit that actually does something, that has charge flow. And the reason why we need that is that the reason why we need an EMF or a battery is so that when the charges go around a circuit, they can be reused. So let's say that you have charge going from one part of a loop to the one end of a loop to the other end of the loop. Eventually it will get back to where it started. But if there's no source of EMF, then the potential that it will have when it gets back to where it started will be lower, because we'll have passed through resistors and things like that. And so we need this EMF to reset the potential of the electrons as they pass through it, because every time an electron passes through, its potential jumps up, and then it can go around the circuit again. So these EMFs are there as like electron recyclers. You can think of them that way. So let's back up a little bit and think about why we might need that. It's this business about electron recycling, but I'm going to give a more explicit example. So let's talk about a charged capacitor and a conductor. Or this is an example. So initially, you just have a capacitor that's just fully charged. It has positive charges on one side, negative charges on the other side, and it's just sitting there. And then we connect the ends of the capacitor up to it through a conductor. So the picture here is you have like a capacitor, and I'm drawing it really big here. You have a few positive charges on one end, a few negative charges on the other end. It's connected by equipotentials, which are not conductors. They don't have any resistance and so on. And then say that there's a switch here. Remember, that's what a switch is. And then we have, say, just a piece of metal that is a physical conductor. It has resistance. So on the left side of the capacitor, you'll have some voltage. On the right side, you'll have some other voltage, and they'll be different because there's a potential difference. And so because these wires are equipotentials, we have a potential difference here, VA and VB. And so when the switch is closed, remember that just means that this equipotential joins with this equipotential. When the switch is closed, electrons from the right side of the capacitor, remember, because electrons flow in the opposite direction of current, because current is the flow of positive charge, but electrons are negatively charged. So you'd have electrons that come off here. Let me back up. When the switch is open, the electrons are just going to kind of be over here, but they can't jump. They can't jump the gap. Even though there might be a force, they can't jump the gap because there's nothing to conduct them. So there are just electrons here. But once the switch is closed, those electrons can actually make it across the gap. And so they'll be yoinked all the way along to the positive end. And so what will happen is you'll have electric charges pass through the equipotential, pass through the conductor, lose energy along the way, and then recombine with their positive charges. Sorry, the negative charges do this, recombine with the positive charges, which reduces the overall charge separation on the capacitor, and therefore reduces the electric potential splitting the two plates, right? And so once so the point is once you close the switch in this example, the electrons are just going to start racing around to meet the other side of the capacitor, neutralizing it. And so the potential difference will just start to decrease. And depending on the capacitance of the capacitor and how charged it was, it will either take a lot of time or take a little bit of time. Generally, for real-world capacitors, it'll take on the order of it'll take either 1 second or significantly less to fully drain the capacitor, meaning for the charges to equalize. And just to be clear, the current flow in this picture is actually counterclockwise. Even though the charges are flowing clockwise, again, current flows in the opposite direction of electron flow. And so the point here is that as the voltage across the capacitor drops, the voltage across the resistor drops, and so the current will drop as well, because the current in a resistor is proportional to the voltage. That's Ohm's law. And so which will then slow the rate at which the capacitor drains, and then it'll continue draining until it'll just slow down exponentially, and we will formalize that later. But eventually, the capacitor will be empty and no more current will flow. So this is why we need a battery. We need something whose potential always stays the same, regardless of how much current has flowed through it. With just a capacitor and conductors, i.e. resistors, you can't really get steady state current or circuit operation. It just doesn't work. So to get steady current flow, i.e. constant in time, through a conductor, and by the way, this is something that we generally want in real life, we need an EMF source. So an EMF source is just defined to be some object which maintains a constant potential difference. That's all an EMF source is. So if I had replaced this capacitor with an EMF source, then it wouldn't matter how much current flowed through it, because the electrons would jump off one end, go through the conductor, and then re-enter the other end, and they would just pass through and gain more potential as they pass through. And it would just go forever. I mean, obviously that excess energy has to come from somewhere. In typical batteries, that energy comes from stored energy in the form of chemical reactions. Like you have lithiums. I actually don't know what's inside batteries. I know that lithium ion batteries have lithium ions. Some chemistry is happening in there that makes these electrons be free. Copper zinc, I think, is used for different types of batteries. Alkaline, there's stuff, lead acid. There's a whole bunch of different types of batteries, but they all use different chemistries. But the point is there's chemical energy that's being drained, and for some of these you can recharge them, not for all of them. You can also imagine like you can generate a potential difference by some sort of mechanical work, right? Like if you have a water wheel that's always turning at the same rate. Sorry. Need to mute my phone. I just get spam phone calls all the time. If you have a water wheel that's always turning at the same rate, maybe you can imagine that motion can be used to separate electrons physically. Like maybe you have a brush that picks up electrons or something, and that can generate a potential difference. So that energy comes from somewhere. It just doesn't come from the separation of charges, at least not typically. No, they're spam phone calls. They're like, your car has an extended warranty. It's the worst. So last lecture, a week ago, we talked about resistors. Just now, we've kind of talked about EMFs. EMFs are very simple, by the way. There's not really a whole lot of work to be done to understand them. We talked about EMFs, so now it's kind of useful to, oh, and by the way, we already introduced the circuit symbol for something with an EMF. It's just a battery. We already talked about that. So before we can continue, because we're going to do some more analysis, let's actually do the circuitry for resistors. So we're going to reapproach circuit symbols again, add to our list of symbols that we know to build circuits with. So First, this symbol you may have seen before. It doesn't matter how many zags it has or zigs. This symbol is a resistor. So it represents a conductor with a non-zero resistance. So every conductor, with the exception of superconductors, I guess, have non-zero resistance, but some have more or less than others. So like if I just took a piece of copper wire, the resistance of that copper wire is very, very small. So we might not even draw a resistor for it, even though it actually has some non-zero resistance, just because it's so small compared to purpose-made resistance or resistors, which have some large and finite resistance, which are you can just buy from the store. You can get something that has a 10 ohm resistance or a 50 ohm resistance, whereas a copper wire might have like a 1 milliohm resistance. So there are different levels. And so most of the time, if it's just a wire, we'll just draw an equipotential because it effectively has zero resistance. But we can still discuss it as if it had resistance by using this symbol. Often we will use this symbol to separate the equipotential aspect of a conducting wire from the resistive aspect. So if you have like a really long copper wire, that copper wire will have a substantial resistance, right? It might have 2 ohms of resistance if it's 10 feet long or something. And so, and that's because the length of the conductor affects the resistance, right? And so you might describe a 10-foot long piece of copper wire as a really long equipotential and then a little 2 ohm resistor at the end. That would be the same as if you had a bunch of little baby resistances the whole way, and we'll get to why that's the case. But so we do that often. So often if the resistance of a real life wire is relevant, we will separate it into 2 parts. There's the equipotential aspect and there's the resistive aspect, and we just put them next to each other. Also, just as an aside here, batteries can also have internal resistance. So a battery is an EMF source, but it also can have a built-in resistance, and that's because batteries are made of real-world conductors, and those conductors have resistance. And so what you might do if you wanted to accurately model using these circuit symbols a real-life battery is you would draw an EMF source, that symbol for a battery. It looks something like this, with 2 ends, and then you might attach a resistor right next to it to indicate that it's an EMF source and there's a resistance next to it. And I'll go into more detail about that in a minute, but I want to continue with the circuit symbols. The next symbol is something that looks like this. Notice that it has bent arms, and that's for a good reason. This just represents an external voltage probe. An external voltage probe. So, this is also known as a voltmeter. So this isn't actually a component in the sense that it doesn't actually interact with the circuit. What you do is you attach either of these ends at anywhere you want in the circuit, and it will measure the voltage potential between those 2 ends, wherever those 2 ends are put, without disturbing the circuit. So no current will flow through this voltmeter, or at least a negligible amount of current will flow through the voltmeter, but it will still give you a reading as to what the potential difference is between those 2 points that you're measuring. Another circuit symbol that we will run into a lot is a circle with an A through it. This is an internal, or quote unquote inline, current probe, also known as an ammeter. Not amp meter, it's ammeter. You dropped the P. So to measure current using an ammeter, it's not enough to just stick these wherever you want and measure the current between those 2 points. If you want to measure the current through a place or through a region, you have to stick the ammeter in between that place where the current is coming from and where the current is going to. So you have to break the circuit and then connect the 2 ends to the 2 ends of your ammeter. And you'll see pictures of this in the future. But basically, the current has to flow through the ammeter in order for the ammeter to measure it. Any current that doesn't go through the ammeter isn't measured by the ammeter. Whereas current doesn't have to flow through the voltmeter in order for it to measure the voltage. Right, okay, so those are the 3 extra symbols I wanted to add. So now you know what those look like. And the reason why it's useful to have these is because often you'll have a few different voltmeters or ammeters in a circuit, and it will be like, what does ammeter 1 read? What does voltmeter 2 read? And so on. It's a useful compactification of an idea. Yeah, I could go get mine, but I don't have a circuit to measure. Otherwise, I would show you. Right. So before we can proceed with resistors and circuits with resistors, we have to do the same thing that we did with capacitors, right? When we were talking about capacitors, it's fine if you just have one capacitor. We didn't need to do all this business with parallel and series capacitors, but sometimes they're Avinash. But if you have multiple capacitors, you need to figure out a way to analyze that. And we should do the same for resistors. So let's just briefly talk about systems of resistors. Hopefully by the end of lecture today, by the way, we will actually get to a very, very powerful technique that kind of combines these ideas of systems of resistors, systems of capacitors, batteries, and everything. So just like capacitors, resistors can also be arranged in series or in parallel. So for two resistors in series, we would draw a diagram like this. Let me use different colors. So we have and then green, and then black, back to black again. And then let's use like purple. Right. So remember, equipotentials are the places where the potential is just some number. It doesn't matter where you are on the wire. So let's call this equipotential over here have potential VA. Green one will have VB. Purple will have VC. And we'll call these resistances R1 and R2. So those would be measures of how much resistance they have in ohms. So the question is, how do we actually figure out what the relationship is between the voltage difference across this whole system, VA minus VC, and the voltage and the resistances and the currents and the resistances and so on. So just like when we were talking about capacitors, we had to establish a constraint. And so when it was capacitors, we said something along the lines of, well, if the two capacitors are in series and the conductors are neutrally charged, then the charges on the two like innermost plates have to be the same, because one will be positively charged, one will be negatively charged. And then because the capacitors always have this equal and opposite charges on either plate, that indicates to us that the charge across, or the charge on each plate, the magnitude of the charge on each plate is the same on all four plates. So we need a similar type of argument for the resistors. But here we're not talking about charge being stored, we're talking about charge flowing. So the constraint that we implement here is we demand that any charge that enters the resistor, any charge that enters the resistor, exits the resistor. And all that's saying is we just want to constrain our system so that there's no charge buildup in the resistors. If a charge goes in one side, it has to come out the other side. And so that result is that the current that goes in on the left, we'll just call it I, that's the same current that flows through the first resistor, which is the same current that flows through the second resistor. Because if you had more current coming in than going out, that would mean that there's more charges coming in than leave, which violates the constraint. So then the question is, what is the total voltage across the total voltage drop across the two resistors? So we need that constraint because otherwise we can't say anything about what happens. And it's less a constraint that like we are implementing, and it's more just how electrons seem to behave. But this is but we needed to justify why the current through each resistor was the same. And this is the best justification that we have. And it's a true justification. Right, so the total voltage drop, the tot, let's say, that would just be the voltage difference between A and C. The charges are leaving at the same speed. Yeah, they have to be. If the charges, if you have more charges entering than leaving, let's say that you have 10 charges that enter per second and only 5 charges that leave per second, then you would have a buildup of charges inside the resistor, and that doesn't happen. Like otherwise, you would leave it on for 5 minutes and you would end up with a supercharged resistor, which would like explode because there's too much charge in it. That has to happen. Right, so the total potential drop is VA minus VC. And so we could break this up into the potential drop across each component. This is just algebraically true, right? I just added and subtracted VB. And so the voltage drop across the entire system is just the sum of the voltage drops across the resistors, because VA minus VB is the voltage drop across the first resistor. VB minus VC is the voltage drop across the second resistor. And we also know that we know how to compute the voltage drop across a single resistor in terms of its current. So the voltage drop across the first resistor is the current that's passing through it times the resistance. And the current is just I. It's the same for both of them. So it's IR1 plus IR2. And so we can factor and we get it's IR1 plus R2. And so what we end up with is we end up with an equivalent resistance, i.e. if you replaced these two resistors with one resistor, how would you get an equivalent effect? Well, the resistor you replace it with would have to have resistance equal to the sum of their resistances. So this is the equivalent resistance for two resistors in series. And we can do the same thing in parallel. So relatively, it's basically the same. So we have, say, blue like this, and then we have a resistor. Oops, I always draw the tail, and I really shouldn't. Then let's have green over here. So we have VA on one side, VB on the other side, maybe R1 here and R2 here. So here, we know that both ends of the resistors, the left ends of both resistors, have to be at the same potential. The right ends of both resistors also have to be at the same potential because they're connected by equipotentials, and equipotentials means that they're at the same potential. So here, we have that the voltage difference is just the voltage difference across each one. It's just VA minus VB. And so V1 and V2 are equal to each other. And so then the question is, what is the current? How do we relate the current to that voltage and the resistance? Well, again, we use the same argument. Any charge that enters the right-hand side also has to exit the left-hand side at the exact same rate. Like that just has to be the case. Otherwise, you'd have a buildup of charge. So what that means is that whatever charge goes into this equipotential either goes up and through this one, or goes down and through that one. And so what we can say is we can say that the current that goes into the system is just the sum of the current passing through each resistor. And that's just because I in has to equal I out. And so the total current that passes through the system is just the sum of the currents that pass through each resistor. And so we can use Ohm's law, which tells us that V equals IR, to relate this current to the voltage, right? And so we get this relationship that the total current is equal to I1 plus I2. We can use Ohm's law to rewrite I1 and I2 as V over R1 plus V over R2. We can do some simplification. We get V times 1 over R1 plus 1 over R2. And then we can divide by 1 over the thing. So we get V divided by 1 over R1 plus 1 over R2. And so we have now that I total is equal to the voltage divided by a number. And so that number would have to be the equivalent resistance. And so we get that the equivalent resistance is, for two resistors in parallel, is 1 divided by 1 over R1 plus 1 over R2. And this is for parallel resistors. And there you go. So we've established the formula for series resistors for equivalent resistance, and obviously these work as you expect them would, so as you would expect them to. If you had 4 resistors all in series with each other, then you just add them all up. If you had 4 resistors all in parallel, you would have 1 over R1, 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, and so on. So it just works exactly as it does for capacitors. It's just kind of flipped. So I just want to make a note here. Resistors are kind of opposite capacitors in that sense. this might just be a nice mnemonic to help you remember which one's which. So for capacitors, we have that voltage is equal to Q divided by C, right? For resistors, we have that voltage is equal to I times R. And so what we see here is that there's a sort of correspondence. If you swap the charge with current, and you swap the capacitance with 1 divided by the resistance, then you can kind of see why it makes sense that for capacitors, if they're in series, they have this like this inverse type formula, and how it's the reverse for resistors. So there is this sort of relationship between capacitors and resistors, how one's kind of the inverse of the other. It's not quite a rigorous analogy, but it is there, and maybe it'll help you remember which one's which. So in the lecture notes that I'm going to post, there's a whole bunch of examples that are in the Young and Friedman textbook. There, I linked to 3 more examples. This is just practice calculating parallel resistance and series resistance and things like that I recommend that you try out. Right. So now that we've talked about how resistors actually work when they're near or when they're connected to other resistors, now we can actually start talking about more complicated circuits. So first, let's talk about internal resistance. So, like I said before, real batteries are made with real conductors. And those real conductors have resistance, and it's measurable. It might be small, but it's measurable. And so this can be modeled using our circuit symbols, modeled in a circuit by an EMF source. I'm going to use the technical language, in series with a resistor. And so the picture is as follows. So you might have in your circuit, you have this black box, which is a battery. And so I'm actually going to use a different color to indicate that it's not an equipotential. So this is just a black box. It's not like those lines are not batteries, are not equipotentials. So in one end of the battery, or so inside the battery, this thing is, I'll label it battery. You have a resistor in series with an EMF source. And then you have 2 terminals. You guys know that batteries have 2 terminals. And then you know that battery's connected to stuff. Whatever that stuff might be, it's connected to stuff on the other side. And so this resistor, we'll call it resistance little r, because it's internal and usually small. And the EMF will have some EMF curly e. So the question is, what is the voltage as measured at the terminals of the battery? Like if you stuck a voltmeter at the 2 terminals of the battery, what voltage would you measure? This thing is called terminal voltage, by the way, for obvious reasons. And I might call it V subterminal. And that's different from the EMF value. So if we wanted to figure out the terminal voltage, well, we would have to, there's going to be some voltage drop. So there's some voltage drop across this resistor so long as there's current flowing through it. So Avinash is precisely correct. The terminal voltage is just the EMF minus however much voltage is dropped because of the resistor. So that would be I times R, where I is the current that flows through the circuit, however much that is, say I. So importantly, what this terminal voltage depends on the EMF of the battery. So this is things like what chemical reaction is taking place inside the battery. It depends on the internal resistance, i.e., how big are your conductors inside the battery? How thick are they? How big is the battery? Things like that. But it also depends. It depends on the outgoing current. Which is strange. You'd think that if you just measured the terminal voltage of a battery, you'd think it wouldn't depend on what's happening outside. But depending on how much current is flowing through the battery, that will affect the amount of voltage drop that the internal resistor drops, and it will lower the terminal voltage. So in fact, if you have a really, really high current circuit, your battery voltage is going to quote unquote sag. It sags under high current because there's a large internal resistance. Similarly, if you have a small current flow through the circuit, then your terminal voltage will be a lot closer to the actual EMF of the battery because this contribution will be small. So this is why, for example, you can put more resistors in a circuit and increase the voltage across the battery. Seems kind of strange, but it's precisely because adding more resistors decreases the current. So there's a good example of this that's in section 3.3 of the Liber text. It's example 3.3.1, and I suggest you guys take a look. It's just on calculating how the terminal voltage changes when you change the number of resistors. There's one section that I'm not going to touch on in today's lecture because we have a lot of stuff to go over, and I want you guys to take a look at it. Like, this is official lecture material. You must take a look because you will be responsible for it. This is the business on fuses and circuit breakers. Fair game for exams and quizzes and so on. And this is just at the bottom of section 3.3. The basic gist of this is that, and you guys have already learned about this in 9b, but it's that when you heat up a metal, it changes length. And it also might melt, right? So if you had a fuse is the name for a very, very thin piece of wire that you pass current through. And the idea is that if you want to prevent, say, a fire from happening because too much current goes through whatever device you're interested in looking at, or whatever device you're interested in protecting, what you do is you put a very, very thin piece of wire between your power source, between your battery or your mains electricity or whatever, and the device. And if too much current passes through that little tiny wire, it heats up and melts and breaks the connection. So fuses are it's a one-use object, but it's a good way of protecting individual devices if you need to. Circuit breakers do something similar, except they're resettable. And the reason they're resettable is because basically you have a bimetallic strip, and so when you change the temperature of the bimetallic strip, it moves. And the idea is that in one position, when it's cool, it completes the circuit. But if it heats up too much because there's too much current passing through it, remember, when current passes through a resistive element, it generates heat in that element, thermal energy. Then the bimetallic strip moves and disconnects from the circuit. So circuit breakers are what you see in a house, and that they basically just go off when too much current passes through, and then you can reset them by just effectively cooling them down or flipping the switch. But there's more details on that you guys should take a look at. Right. So I'm glad that we got here because now we have to talk about famous, and if any of you guys are EEs, famous Kirchhoff's circuit laws. So these are probably some of the most useful things that you'll see when it comes to circuits in this course. They generalize all the way to the end of the quarter, and they are remarkable and make things super nice. So first, we need to indicate why we need these at all. So turns out that you can't always solve, put that in quotes, a circuit with parallel or series decomposition. You might think that you can always just simplify and simplify and simplify a circuit until it's just series and until it's just one resistor, but it turns out it's not possible. So let me give you a few examples of where you can't do this. So let's say that you have a battery, let me draw it a little bit smaller. You have a battery, and then you have what's called it's a something bridge. A bunch of resistors hooked up like this. And you have R1 and R2 and R3, and then R4 and R5. It's just a width. It's a W/width. It's an abbreviation. Yeah, the other word is laws. Yeah, it's the diamond of resistance, right? So you can't break this down using parallel and series resistors. And the reason for that is because no two resistors are in parallel or series with each other. Like every yeah, it's just not the case. Another example would be when there are multiple batteries. And by the way, remember, a battery can either have 4 or 6, or it could just have 2. So I'm just going to use 2 because it's smaller. If you have a resistor here, and then a resistor here, and maybe you also have an extra battery just sitting there, just because. And maybe you have a resistor here, and then maybe a battery in reverse here, and so on. Like, can't use parallel or series decomposition there because they're not in parallel or series. Or what if you have resistors and capacitors together? Well, a resistor you can't just use a formula to replace a resistor and capacitor in series with just either a resistor or just a capacitor. It'll always be both. So like if you have this, and then you have a resistor here, and then maybe a capacitor, and then maybe just for kicks, maybe you have another resistor here. None of these resistors or capacitors are in series or parallel with each other, so you just can't do it. And so you need more powerful tools. And so the way that we handle these systems, these more complicated systems, is very similar to the way that we derived the rules for parallel and series resistors and capacitors. We just apply charge and/or energy conservation. So I'm actually going to write potential conservation, but really we're conserving potential energy, and that's because there's no mechanical energy here. Or we're conserving potential plus thermal energy, really. Oh, that was a rumbly tummy. Must be hungry. So I'm just going to describe what we can get, and these are these circuit laws. So the first and perhaps most basic of these laws is the junction rule. So the junction rule is literally just a restatement of charge conservation. So charge conservation suggests that whenever a charge exits one equipotential, it enters another. It goes somewhere, and that's assuming that there are no capacitors present. So the junction rule basically says that the current into a junction, and a junction is just when a whole bunch of equipotentials meet, and I'll draw a picture in a minute. The current into a junction equals the current out of the junction. We'll put a box around this. This is a big deal. Very useful rule. So just as a quick example, let's say that you have a complicated circuit and you have you have 5 equipotentials that all meet at a point, just because it's some complicated circuit. And you have some current I1 that's going this way. Maybe you have a current I2 that's coming this way. Maybe you have a different current I3 that's leaving. You have I4 that's coming in. And then maybe you have I5 that's leaving, right? There's just there are currents coming in from all over the place, and they just all happen to meet here. So the junction rule just says that you have that all of the currents coming in, I1 plus I2 plus I4, that's the total current going into a junction. That's equal to the total current that's leaving the junction, I3 plus I5. It just says that any current going in is equal to the current coming out. It's a very powerful tool, though, because it lets you relate different currents at 3-point or more mergers. Like at a point like this, that would be a junction because you have current coming in from 3 different places. The junction rule obviously also applies to 2-point junctions, but those aren't particularly interesting because the current coming in only has one way to go. The second rule, a little bit more complicated, is the loop rule. So the loop rule is effectively energy conservation. So energy conservation suggests that in a steady state circuit or a steady state network, the energy any given electron has doesn't change if it starts at one place, goes around the circuit, and ends back up at the same place. And the reason that has to happen is that if the energy changed after going around the circuit just once, then it wouldn't be steady state, because then it would have less energy to do it again. And so something would be changing with time. And so the loop rule is really saying that the change in potential energy of a single electron or a single charge around a loop is 0. So, but we can decompose this into more circuit-friendly ideas. So for a charge, the potential energy is just the charge times the voltage. So that means that the loop rule, that the change in potential energy over an entire loop is 0, this just becomes that the change in potential across a loop is 0. And so the loop rule, in words, is that the sum of the voltage drops or gains around any closed loop is 0. Put a box around that. It's important. So that's the loop rule. So the example here would be something like, let's say that you have a battery, and then you have a resistor, and you have another resistor, then you have, and then they're just connected back up. And let's say we have, let's say that we want to add up the voltage across a counterclockwise loop. So we would pick a spot to start. Let's say VA is the potential there, VB is the potential here, and let's say VC is the potential here. Those are the 3 different places that there could be different potentials. So this would say that VB minus VA, or actually we should probably go in reverse because we want to talk about voltage drops. No, we can do it this way. Yeah, that's fine. So VB minus VA, that's the voltage. So we're starting at VA, and then we're going this, and then we're going to go in a clockwise loop. So we're going to add up the voltage drops and or gains as we go through the loop. So VB minus VA plus VC minus VB, that's the voltage across this element. It's the voltage change between these 2 points, plus VC minus VA, that adds up to 0. And if you check, obviously this adds up to 0. But the reason why this is a useful tool is because we can relate things like the voltage across a resistor to the current. And so we wouldn't just write VC minus VB there. We would write something like IR. But obviously, the voltage across these, the sum of voltages has to add up to 0, because the voltage here just is whatever it is. The voltage here is just whatever it is. So in the lecture notes, again, the ones that I'm going to post, there are a lot of details and examples in the link that I provided. I think it's section 10.3 in the online book, because you have to go in order. So from VC to VA, the voltage drops by, or the change in potential is VC minus, sorry, no, you're right. It should be VA minus VC. I just got it backwards. Because you do final minus initial. Yeah. Okay. So, and I linked to this. There's just a really long detailed page that I suggest you guys read, just so it'll get firmer in your head. Right. So now let's just do some examples so you guys can see this in action, because this is going to get tricky and you're going to be doing this a lot. Like in discussion next week, you're going to just do this basically. So let's do some problem solving. Do some practice. So we're going to work by example. I'm just going to draw a relatively straightforward example, and we're just going to analyze it. So let's say that we have a battery, and then we have another battery that's oriented the same way, but below that battery, there's a resistor. And maybe there's a resistor connecting these 2 points too. And just for good measure, let's put a resistor here. Label everything appropriately. So we have an EMF here, we have an EMF here. We're going to assume there are no EMFs for, or there's no internal resistances necessarily. It depends. We can talk about that afterwards, but let's call this R2. Let's call this R1. Let's call this R3. So there's EMFs here, there's resistors, so there's going to be some current here. And what that current is will depend on what the resistance is and what the EMFs are. But solving this circuit, in air quotes, solving this circuit amounts, God, I'm getting so many phone calls. Solving this circuit amounts to answering the question, how much current flow, or how much, I should use the word current, flows through each resistor and or each EMF, but that's a little bit easier to figure out, and which direction. So that's what we're going to try to do. We're going to try to come up with a set of equations that will let us solve for that. So first what we should do is we should label the circuit with currents. Just give them names. Just that way then we have variables to solve for. So I'm actually going to take this and blow it up really quick. Just that way then it's a little bit easier to work with. Bet you wish you could do that on your, well, you guys are probably using things too. So I'm going to call, so we know that current never changes unless there's a junction, right? The only time that current can change is when it's passing through a junction. So the current that's going this way is going to be the same as the current that goes up that way, which is the same as the current that goes to the right, right? All of those currents are the same. So we're just going to give them all the same name. I'm going to label that current, and I'm just going to guess a direction. I'm just going to call that current that flows in that direction, I'm going to call it I1. I'm just going to guess another direction for the current that goes up the side here. I'm going to call this current I2. And then I'm going to call the current that goes up this side I3. Again, these directions for the actual current are completely guesses. They probably don't go in this direction. In fact, they probably, like I2 and I3 certainly goes downwards, and I2 probably goes downwards depending on, well, it might go downwards depending on which one has a larger EMF. But it doesn't matter because regardless of what direction we choose, it'll work out at the end of the day. So let's just stick with this and see what happens. So now we can apply the rules to this circuit. So first, let's apply the junction rule because it's super easy. So the junction rule, and there are only two junctions here, right? There's the top junction and there's the bottom junction. Now, we know that the top junction, there are three currents that all go in, right? So I1, I2, and I3 all go in. The bottom junction has three currents that all go out. I1, I2, and I3 all go out. So in both cases, you'll have 0 equals 3 things added together. So let's just use the junction rule for the top junction. And you would find if you did the same thing for the bottom junction, you'll get the same equation. So we're just not going to bother doing it. Because by the way, at the end of the day, we're looking for a set of algebraic equations that we can solve. And so if you have two of the exact same equation, it's not useful. So the junction rule applied to the top junction would give us that I1, because that's coming into the junction here, is added to I2, that's also coming into the junction here. And that's added to I3, because I3 is also going into the junction. And that should be equal to 0. So automatically, this should indicate to you that one of those currents should be negative. And all that means is that one of the currents was in the wrong direction. It's probably I3. But the point is if you get a negative current, it just means that your guess for the direction of the current was the wrong one. And so you can just adjust it so that the current is in the correct direction, and then you know the magnitude, how much current is flowing through. So, okay, I'm going to put a box around that. That's one of our equations. We only need 2 more, right? Because there's only 2 variables. So now we have to do the loop rule. So the loop rule is quite a bit more involved. So you might ask the question, which loops do we use? Because the loop rule is a statement about any closed loop. And you might think that you need to pick a particular loop. In fact, in this circuit, so the current is almost a vector quantity. We would say that, so current isn't quite a vector quantity, it's really just positive or negative. but we say that current is positive opposite the direction of electron flow. So if we say that, so if you find that the current is negative, then that's in the direction of current flow, but we define current to be opposite the direction of current flow. So that's why you would have to change the direction in your model of what direction of the current flow. That's all. The idea is that current should just be a number. It shouldn't be a vector. It's just if current is negative, it just means it's flowing in the opposite direction from the direction that you thought it was flowing. Hopefully that helps. Yeah, yeah, correct guess of direction will be positive. That's a good way to put it. Right, so the question is, which loop do you pick? So there are 3 loops here, right? There's a loop that goes all the way around. That's one loop because there's a loop there. There's a loop that goes around the rightmost square or the right rectangle, and there's a loop that goes around the left rectangle. So the question is, which ones do we pick? So each one of those equations, or each one of those loops, will give us an equation. It'll give us a sum of potentials equals 0. So if we're clever about this, we can figure out how many loops we need to pick. We only need to pick 2 more because there's 3 unknowns, 1 for each of the currents. We already have 1 equation, so we don't need all 3 loops. We only need 2 of them. So we just need to pick 2 of them and stick with it. So I'm going to lay out the steps for the loop rule that we're going to follow. So step 1. So once we've picked a loop that we're going to try to find the loop equation for, you have to choose a loop direction. Now, often that loop direction will be easy because you can just pick the direction that kind of aligns with your guess of current. But sometimes, like in this case, the currents don't really flow in a single direction, right? We guessed our current I2 is opposite the direction of I1 if we were talking about the leftmost loop. So there's not like a correct choice for the loop direction, and it doesn't actually matter which loop direction you choose. You just got to pick one. So you choose either clockwise or counterclockwise or anti-clockwise for those of you who are in the Anglosphere, but we're in the Anglosphere, so, well, whatever. Step 2, choose a starting place or choose a starting point. So you just need to pick a place on the loop that you're starting from that you then walk along until you get to the end. And really, you can choose any point on the loop, but it has to be in the loop. You can't pick a starting place that's not in the loop that you're interested in. Step 3. I'm going to put walk in quotes. You walk around the loop, adding up voltage changes as you move or as you cross them. So depending on what you're passing, the potential difference or the voltage change will be different, right? So for a battery, how does the potential change if you cross a battery? Let's say that we started here and we wanted to cross the battery going up. Well, how does the potential change between, say, this point and that point? Well, the potential goes from low to high because the potential on the positive end of the battery is higher than the potential on the negative end of the battery. So in that case, when you cross a battery or a capacitor from the negative to the positive sides of the battery, you add the EMF. And that's just because the change in potential, the final potential minus the initial potential, is positive, and it is equal to the EMF. If you instead go from the positive side of the battery to the negative side, if you're crossing it the other way, then you would subtract the EMF because the initial potential is higher than the final potential. So from positive to negative, you just subtract the EMF. Should make that bigger. So, and by the way, this applies for a capacitor as well, because the capacitor has some fixed potential difference across it. That's calculated by Q equals CV, so you can solve for that potential difference. And so when you go from the negative plate to a positive plate of a capacitor, you add that voltage. When you go from a positive plate to a negative plate, so you subtract that voltage. For a resistor, in the direction of chosen current flow, so remember, you had to pick a direction of current for each of the currents. So if you're passing a resistor in the direction that you chose the current to be, so let's say we're doing this loop again, that would mean passing by R1 in the direction of current flow. So that would be the example that we're talking about here. So if you pass a resistor in the direction of current flow, then you subtract IR. And that's because we know how much the voltage changes by for a resistor. It's the current times the resistance. That tells you how much the voltage decreases by. So the voltage decreases, so that's why we subtract IR. And the magnitude is just IR because that's Ohm's law. And so for a resistor in the opposite direction, the direction opposite of current flow, you just add IR. And that's because if you were going opposite the direction of current flow, say this way, assuming the current is positive, meaning that that is the direction current actually goes in, the voltage that you started at is lower than the voltage that you're ending at, because the voltage is always lower after current passes through a resistor rather than before. Sorry, the voltage is lower after current passes through a resistor. So you just add IR if you go against the current flow for a resistor. And then step 4. And by the way, we will add capacitors to this later. At least for now, capacitors are relatively easy to handle because you just treat them like batteries, at least when we're talking about study. I mean, yeah, this is convention, but like, it's a reasonable convention, right? Like, why would you, like, it's convention to define the change in something as final minus initial. You could have defined it as initial minus final, and that would work just as well, but everybody has agreed that delta means final minus initial, so that's what we do. So step 4 is we set the sum to 0. And then that gives you an equation. You have a whole bunch of things that might involve currents, that might involve resistances, that might involve EMFs, all added together, and then you get 0. So let's apply that to the left loop. Let's do the left loop first. So this loop. So I'm going to redraw really quick. So the left loop has the following. So we have a battery. I'm going to draw it kind of big, and I'm just going to isolate that loop because we don't care about what's happening elsewhere. And then we have another battery, and then we have a resistor. And then we have, and I'm going to put some legs coming out to indicate that there's other stuff, but I'm just not going to draw it. And we have a resistor. So we have R1 here, R2 here, EMF 2, EMF 1, and we have chosen I1 to run this way. Oh, let me use a different color. I1 runs that way, and I2 runs up. The reason we don't have to worry about I3 is because it's not in any of the wires on the loop. So now we have to pick a starting place. So let's pick a starting place. Let's call that, oh, and let's choose a clockwise loop. We'll use a different color. So let's do this loop. Let's calculate the, let's do the loop rule for that loop in that direction for that circuit. So, okay, so let's start here. It doesn't matter where we start, we just got to start somewhere. So we start and then we move along our loop. So the first thing that we do is we're at an equipotential, so nothing happens until we get to the battery. So when we get to the battery, we're crossing the battery from the negative terminal to the positive terminal. When we do that, our rules say that, and our sensible reason says that we should increase the voltage. Our delta V is positive. So we add plus E1, that's our first term. Then we meander along, And then we want to stay inside this loop. We're not going to the other part. We're staying inside our loop. And so we go down and we encounter another battery, the battery with EMF E2. But this time we enter that battery from the positive terminal and go to the negative terminal. So then we subtract that EMF according to our rules. Then we proceed along. Now we exit that battery and we enter the resistance or the resistor R2. But note, we are entering that resistor opposite the direction of the chosen current flow. Current flows through that resistor upwards. At least that's what our guess says. And so we need to add, because it's opposite current flow, we need to add the voltage drop from that resistor. So that would be plus I2 times R2. That is that's the voltage drop across that resistor, where the voltage is lower where we started and higher where we ended. Hence, we're adding. Then we finally get to this resistor R1, and there the current flows in the direction that we are moving, that we're walking along our loop. And so then we subtract I1 R1 because the current flowing through that resistor is I1, the resistance is R1, and so we multiply them to get the voltage drop. Step 4 then just says set them all equal to 0. So this is one of our loop equations. And now we can do the same thing for the rightmost loop. Now we just had to choose some loops. I'm choosing the left loop and the right loop rather than the big one, just because. So let me reproduce the rightmost loop now. So we have the EMF, E2. Then we have our junction, which maybe has stuff coming in from the other side. Doesn't matter. Then we have our resistor, another resistor, and that's it. So we have current flowing up this way, I2. We also have current flowing up this way, I3. Should label this R3, label this R2. And I'm going to use a clockwise loop starting from that junction. So let's do the same thing for this loop. So starting at that junction, the first thing we encounter is the resistor, which is again, the choice of current is opposite the direction of the loop direction. So there, we add the voltage drop across, or we add the voltage gain across that resistor. So plus I3 R3. Then we continue our loop around, go around the bottom, come around the top. We encounter the resistor. This resistor R2 has current flowing upwards, and we are going upwards, so we subtract the current, minus I2 times R2. And then we encounter a battery going from negative to positive, so we add that battery's EMF, and then we're back where we started, so we set it all equal to 0. And that is our third equation. So now, oh, we're going to finish early today. So now we have 3 equations. So the 3 equations that we have are I1 plus I2 plus I3 equals 0. That was our junction rule equation. Our second equation from the first loop that we did was E1 minus E2 plus I2 R2 minus I1 R1 equals 0. And then we have our third equation, I3 R3 minus I2 R2 plus E2 equals 0. So we have 3 equations, assuming that the EMFs and the resistances are known, that there's only 3 unknowns. Like this would be, and by the way, it'd be fairly typical to be given the EMFs and the resistances, because those are just like parts that you buy off the shelf. And if you wanted to figure out what the current would be when you assemble it, then you'd have to do this sort of calculation. But so now there's 3 equations and 3 variables, and you can just solve. This is just algebra at this point. Sometimes the algebra can get messy. So there is something to be said that as you get more experience with these things, you'll get better at picking the good loops or the good junctions to use these rules for to reduce the algebra load. But in general, as long as you pick enough independent choices, enough independent junctions or loops, it doesn't actually matter which ones you choose. You'll just get some set of algebraic equations that you can then solve. There, I did use the word independent when I was talking about independent equations. The reason I did that is because there's something to be said that if you pick, like, for example, if I had just chosen to do the junction rule twice, here and here, and just ignored what they actually looked like, I would have just gotten two identical equations for the junction rule. And that doesn't actually count as two equations because they're identical. They're not independent of each other. So you have to be a little bit careful to make sure that you're picking independent rules to apply. But for the most part, if you accidentally pick two rules that are actually dependent on one another, then you'll know at the end because you won't be able to solve for what you're solving for. And then you just have to go back and find another thing. There will always be enough, well, I shouldn't say that, but there's only so much information given in a circuit diagram. So regardless of which loops you choose, which junctions you choose, you will always find exactly all of it, assuming you don't pick any, you don't make any mistakes and pick dependent ones. Jennings asked, why is that last equation has positive sign for E2? It has positive sign for E2 because we crossed this EMF, this battery, from the negative terminal to the positive terminal. All right, so that takes us all the way through to 126, which is perfect timing, I suppose. We're ending a little bit early. So I will stop the recording.